Hey guys, welcome to this page of the notes. And so now what we're going to do is, now that we've had an opportunity to sort of review angle bisectors, let's go ahead and take a look at our second point of concurrency, which is going to be the in-center. Now, it's like I said, it's going to be really easy to sort of begin to get these points of concurrency mixed up. We already talked about a circumcenter. Let me first talk to you about the in-center. We'll talk about what it is, how you find it, and then we're going to kind of work through together similarities and differences between the two to try and help us keep these 2 points of concurrency, circumcenter and in-center, straight in our minds, right, so that we don't start jumbling them up. It is tricky, believe. I know it's a lot of information and it's difficult to keep it straight, but that's really going to be your job, making sure that you review this enough times, whatever you have to do to help keep these terms and their definitions straight, because I will, if you're taking this class with me, I am going to test you on them. So the in-center, here we go. In-center is going to be based on finding the point of intersection of angle bisectors. Now I know it might be a little difficult to see on my diagram, so let me go ahead and do these in red. I have, right, it's a triangle. I have 3 angles, angle A, B, and C. I have 3 vertices. I'm going to then draw 3 angle bisectors. The angle bisector of A, the angle bisector of B, and the angle bisector of C. I'm looking for the point of intersection of those 3 angle bisectors. That point of intersection is going to be what we call the in-center of a triangle, where the angle bisectors meet, their point of intersection. Now, what's important about the in-center is this. The in-center will be equidistant from the sides of the triangle. That means the distance from in-center to point X, the distance from the in-center to point Z, and the distance from the in-center to point Y. All of those green lines are congruent. They're all equal to each other. That is our in-center theorem. The theorem says as long as you find the in-center, you are at a point that is equidistant, the same distance from all of the sides of a triangle. Now, why do we call it an in-center? Well, here we go. Let's talk about the first difference between circumcenter and in-center. Remember, with the circumcenter, what we did is we had a triangle, and the circumcenter was a point. And again, I'm freehanding this, so please forgive my drawing, especially when it comes to circles. But the circumcenter was a point that if I drew a circle where the circumcenter was the center of that circle, the circle would completely go around the triangle. The entire triangle will be inside the circle, and only the vertices will touch the circle. Sorry. Again, I know. It's freehanded. The idea is this. Circumcenter, a circle goes around the triangle, and just the vertices of the triangle touch the circle. Right? That's circumcenter. The circumcenter is the middle of a circle that when I draw that circle, the entire triangle is inside the circle and only the vertices touch the circle. Now, in-center. In-center is going to be where you are drawing a triangle. Oh, too much. There we go. Do this one in blue. The in-center will be the point that if I make that point the center of a circle, I'll be able to draw that circle entirely inside of the triangle. So it'll be a circle that is completely inside of the triangle and will touch the triangle, right, at 3 points. Each will be equidistant from that guy. Again, I'm drawing a circle which is by hand, which is not going to be perfect. Anyway, there we go. So now the in-center, it makes sense, in-center, inside the circle. I can draw a circle inside of the triangle where the in-center is the middle of that circle. And the point is this. each of those radiuses then of the triangle, right? That radius, of course, is the same as that radius, of course, is the same as that radius, right? And each of those radiuses is going to be where the circle is tangent to the side of the triangle. And because it's a circle, right, each of those distances has to be congruent, right? The radius of a circle can't change or else it wouldn't be a circle, right? So the idea is simply this for an in-center. You can draw a circle inside of a triangle, and what is going to happen then is each of the sides of the triangle are now equidistant, the exact same distance from that in-center. So there's the first distinction between the circumcenter, which we talked about in the previous section, and the in-center in this section. Another distinction is this. The way that I find the in-center is angle bisectors. Angle bisectors. The way that we find the circumcenter was perpendicular bisectors, right? So perpendicular bisectors to the sides of the triangle will find you a circumcenter. Angle bisectors will find you the in-center. All right, really important that you can keep those two straight. So let's talk about our first problem that I've got for you guys right here. I give you a triangle, RST, RST, and I've given you 2 points, P and Q. I want to know which point is the in-center and explain, which point is the circumcenter, which point is the in-center, and how do you know? This is actually a really, really important idea right here. Remember that the in-center is angle bisectors. Angle bisectors. This is a really, really important idea. What that means is this. In-center is found by angle bisectors. When